Okay, guys. Today we start next action, space and time 13. Huh?
You got a new shirt?
And okay. Okay. First of all, the questions. Do you have any questions for the previous ones? Everything is set?
No.
No. Okay.
No,
So,
we do. What's it? No, did I ask?
Well, it's okay.
Oh.
I asked.
But did I have another? What was the last
Gotcha.
question? I'll ask that
Gotcha.
one. Oh, okay. Never mind.
never mind.
Yeah, never mind.
No questions. Okay. Okay. So today it's important lesson. We will talk about energy, which you at least heard something about it. Mostly kinetical, but some other forms of energy. Work. This is the new term for you. In physical work, mechanical, and information. Those things are very closely related. Believe it or not, we live in an informational age, and we live also in the world of lots of so-called heat engines, like the gas engine in your car is a heat engine, right? And lots of steam engines, rockets, and the most famous of heat engines is Kalashnikov. It is the most famous assault rifle in the world. It is a heat engine too. All of them are heat engine. Yes.
Aren't we in the emergent age?
We live in energy age and informational age.
Oh no! Wait, but information age was the first computer, so aren't we in the emergent age?
This emergent? You mean the beginning?
No.
What?
No, emergent is like now, with the new technology.
Actually, you know what's happened? We'll talk about this today, right? But what happens that we only start understanding that actually whole thing around us is informational. The nature of nature, right? It is closely connected with information. And only now we're starting to understand it. We are coming to this step by step. Like for example, to the main ground how to say it, this fundament, right? The most fundamental theories of modern physics, like this is quantum physics and relativity physics. They are very closely connected, but not officially united yet. That I am working on this. Probably you know, maybe heard about it. But it is officially in official science. They are not united yet, but they are both as like two stones on which the whole physical theory is based. And it was found in the beginning of the 20th century, so more than 100 years ago. It was found that actually both of them are theories of information. Relativity theory is about signals, and signals carries information from information carried by signals. This is relativity, and quantum mechanics is about measurements. Again, getting information from certain recording and everything. So yeah, what's the question?
That's not what I meant. I thought you meant the era and technologies. Because I thought you meant era and technologies, not the type of information which we work with. I meant like the era and time of which of research that
No,
we're in.
they call this epoch, like in common sense, they call this time which we live in informational era, or information of IT era.
Oh, I did that.
Yes.
That was the 20th century. We're in emergent age. It's with the all new technologies, drones, very high tech drones.
High tech what?
Drones. That's an emergent age.
You know, maybe Antosha, maybe you can explain. I'm not getting what Viti is asking.
I think you're talking about two different things. It is talking about the age of technology which we're, and they call it the emergent age. But this is different from what you're talking about. I don't think it's relevant.
So can you explain it to each of them later?
Fine.
Because I'm not getting the question. Okay. Okay. So we'll continue for now, right? So okay. So energy. Okay. So energy is actually, if you talk about energy is something that looks like very well known in physics, right? Everybody talks about energy, not only in physics, in our common life, right? The sources of energy like oil, gas, nuclear energy everywhere. But interesting enough, that the real concept of energy is missing. Physics has some understanding that energy is some potential something, the potential to do something. So to produce some changes, sometimes useful, sometimes not, in our world. Like energy in a nuclear bomb can produce a lot of destruction, right? So they're changes, right? And changes can be measured in a certain way. So how we measure the changes? The most scientific way, you would say, the amount of changes are measured in bits, actually. So what is the change? It's that something can go two ways, in a simple way, simplification. Where something goes two ways, like the thing can exist or does not exist. For example, two ways. So, and if we see that the thing is there, we have one bit of information. So the changes are measured in bits, because every change, whatever complex is it can be divided into pairs, right? So this change, that change, like in doubles, right? 0 and 1, yes or no, false or true, whatever. So you can divide anything in these things and then measure, and the measurement is in bits. So, like generally speaking, energy is as a potential to make changes. It is a potential to actually to produce information too. So, from the very general point of view, we already can see some similarity between energy and information. What was the question, Vitya?
I thought you said something different from what you said, but then I thought you were talking about like qubits, like you can exist and not exist at the same time.
No, come on. Qubits, we're not talking about qubits at all. You may talk with your dad about this. We are not talking right now about it, right? These are only bits. We're talking about mathematics of this and some physics. It's more partly classical, partly quantum. But nothing has nothing to do for now with qubits. So just don't mix them. This is just bits, One yes or no, 1 or 0, anything like this. Okay, so
Guys, I love you.
So first of all, we'll start from the classic physics, and we'll find out what is work. Definition of work in physics, in mechanical mostly, but not only mechanical, like mechanical work mostly, but anything. The definition of work is the amount of energy, that is transferred from one object to another. So one object 1, and another object 2, like the balls that you had in the previous lecture, right? So one ball hit this, or anyhow interacts with the other object, one object 1, and object 2, whatever objects are. So it interacts with this, like for example hits, and transfer, so put some energy into it, from here to here. And the amount of energy is transferred, it is called work, or like W, work. So it's an amount of transferred energy from object 1 to object 2, or back, whatever.
Did you write this down?
Okay.
Wait, it's done.
So work is a transfer of energy. And I don't want to go too far into it. We'll be finding out it step by step. But in the beginning, we'll try to write how it goes. Like for example, we have some movement that is that something is moving along axis X, right? And it is moving because this object which is moving, right? It is moving by the force like F. It is a vector, but anyway, and along one x, it is just f. So this is moving, and when it passes some interval, right? It produces, because definitely it is some energy spent in this movement, right? It produces some work. So what kind of work can force F produce by the path like x, for example, on this x? So how do we find it? If you remember this definition of derivative, so we want to find the change, the rate of change, how energy changes along this path. When something, this object is moving along the path, how the energy changes, because the change of the energy, it is work, right? It's transferred somewhere. We don't want even to know where it is transferred. So if we do that, we remember that kinetical energy is mv squared divided by 2. Remember that? So this is object with the mass m, right? So how we do? According to the laws of derivation, like we can write it make a little trick. We do not make derivative by x, by dx, right? By first, because we know this formula, right? And we see the variable is v here, not x. V of the object, the velocity, right? It depends of the path. Maybe there is friction, maybe something. So it is a function of x. But we don't use it directly. We just see that variable is v here. So first we write this equation, dE by dV. So not dx by dV. But we want to get this, right? So dV, then we should write dV by dx. Oh, sorry, not dV. We write dV by dt. Again, you see some trick. And here we write dt by dx.
Where did the T come from?
Oh.
No, it's just a trick. Remember, it's mathematical trick, but it's a legal one. So you see, you can, как это сократить? We can do that and that, right?
Cancel out. Yeah.
Cancel out. We cancel out dv, dt, and we have the same dE by dx. You see? It's a trick. It's a mathematical trick.
They cool.
But it's legal. So think about it, how it's done, right? But the end is like this. So dE by dx equal. This is, we can make a derivation from this formula by dV. Can you calculate how much would it be dE by dV?
But they don't remember. They don't remember. MV.
Okay, so if you dA by dV, it is mv. Now dV by dt. Do you remember what is this? Speed change. Huh?
What's the change of speed?
Change of speed. What is it?
Thank you, Vita.
Did acceleration?
So this is mv, or it is a momentum, right? We can write momentum, but this is mv. We calculated it from here. Now dV by dt it is, again?
Got that. dV over dt. Say it.
Acceleration.
Acceleration, right. Nice, Katya. So this is acceleration. We remember we noted as an A, right? So it is A. And now dt by dx. What is it? Any clue? What do you think? What is dt by dx? What do you think? What can this be?
But X is like that. What did
Hold on. Vita, wait. Answer Dennis' question. What is dt over dx? What is dx over dt? X is what? Distance. T is time.
Oh,
Got that?
Oh, it's X is distance, time.
X divided by time. Distance divided by time.
Speed. Oh, it's
Thank
speed.
you.
So then if you switch it around, it's seconds.
No. It's speed, but it's 1 over speed.
So it's inverse.
Then it's 1 over v.
It's, yeah. So this is v minus 1, or again 1 over v. Exactly. So this is 1 over v. So inverse to the speed. So 1 over v. And v we can cancel out here, right? We have ma. Do you remember what ma is?
And is
If you
what's a again?
Acceleration.
second law of Newton's law.
Mommy, it's empty.
Mass.
Mass times acceleration equals
What do you need to do to create acceleration of an object?
you need a force.
This is actually a law.
Then it's force.
It's force, exactly. So this is the second law, and this is force. So now we have dE by dx, or we can write it like this. dE equals F from here and here, right? dE equals F by the multiplied by dx. And this is actually this, because this is the change of energy. So this is exactly what we call force, change of what we call work. It is F dx. So this change of energy or work, it is force multiplied by the interval of space.
Oh.
By the way, there's another interesting formula, that is dP is actually F dt. That's another formula which comes from, actually this is another formulation of the second law. dP by dt, it is ma. dP by dt, P is momentum, ma. P is ma. Mv. Sorry. P is mv. So change of mv, it is mass by acceleration, and this F dt. So they are very looking, just this is space looking the same. Just this here is space, and here is time, and here is energy, and here is momentum. And this is very significant, because actually in the theory of relativity, momentum and energy are the both opposite sides of one thing, which is called momentum dash energy. The same as space dash time. Space time and momentum energy are very similar connected things. So momentum and energy are connected the same way as space connected with time. But just for you to maybe to think. And these formulas, it shows the similarity, by the way, too. So now what we see again, that the change of the work, right? So the change of energy transferred in the process, it is force multiplied by space on which space interval, on which interval the force is applied. So here, right? So we apply force to some object during this path, and on this path, this force produces that kind of work. This is just right to remember. This is one of the main things regarding definition of work, mechanical work. And of course, if you see like that change, like again, I write it, dV equals F dx, and if F is constant, so if F is constant, if F does not change, we can make an integral of this, and this will be, so summarize this, F dx, and F, because it's constant, we can write it like this, F dx. And integral of dx, you can remember, maybe not, but it's just x, just interval, on which this force is applied. So, and this is work, total work, because integral of dV, this is work. So the simple, when F constant, F means F, x. Very simple. When f is constant. Where f can be constant, like the simplest things, for example, if you have, again, this movement object, right, and it has friction force, like friction force, and we're moving to x, from 0 to x, right? The friction force is not changed. Some constant thing. So the work that this force produced on this path will be exactly F by x. Another example with the same formula, if F constant, which is important because it's simple, right? We have ground, right? And we have some object that we are lifting to the distance h up there. To do this, we should apply the force which is equal to the weight of this object and on the distance h. So the weight of this object, it is equal for the force, it is m multiplied by acceleration. G is acceleration of the Earth gravity, remember? 9.8, yes, meters by second squared. So F mg, right? So, and F is constant because it's if it's not that far from Earth, it's still the same. It's mg, and that's all. So you can calculate which would be the work produced by this force to get it to the height h. What would be? It's force multiplied by what work we did when we lifted object to the
Right over here.
There?
Over here. Yep.
this is the path.
Did it dx?
F multiplied by
Take a look. What do you see there? It's literally the only thing you see there. Is it? Do you see G on the diagram?
No, it's H. Did it H?
h, right? And it is mgh, right? Because the force is mg. So we made some work, lifting this object with the mass m to the height h. Where this energy go? It is transferred to something. What do you think? Where it goes? The energy we spend some energy when we're lifting this thing. We spend some energy, and the energy is this, right? And the work is this, mgh.
Potential energy.
What energy?
Potential.
Potential, exactly. It is called gravity, potential, or gravitational, right? Gravitational potential energy. There are other types of potential energy, like in electric fields and other fields, like nuclear fields, whatever. Many potentials. This is gravitational potential energy, right? And this is like this. So it is Eg, you may write it Eg, E gravitational, right? So, and the same thing goes when you let it go, you put it up and then you let it go. It will fall down. What energy will it produce when it fall down?
It will produce kinetic energy.
It will produce kinetic energy, right? It will be, and you can calculate it, right? It will be, you can calculate it like this. Kinetic energy equals to this energy, right? Equals to mgh, right? Right? So from here we can calculate speed, velocity, right here.
Oh.
Right? Right. Yeah, you're right. That's okay. So it goes down, then it hit the Earth, and it stops here. What happens here?
Well, it'll bounce up.
Huh?
Did
It will bounce. Yeah, it may bounce if it is elastic collision, remember, right? And if it's totally inelastic, so just boom, and it stick here, where the energy goes.
Well, it's preserved.
Yeah.
Because nothing happens.
What happens when two Play-Doh balls smack each other?
Yeah, they are smashed. But for example, maybe it is not this kind of.
Then it turns into heat.
Right, exactly. Yes. Okay. And now we'll talk a little about heat. A little, just a little. What is heat? Heat is an energy. It is called thermal energy. Another type of energy. Thermal. Thermal energy. And thermal energy, which is found from physics, it is actually energy of moving molecules. So like any object, like for example this ball that not ball, maybe a brick, which hit the ground, right? It contains lots of molecules, right? Or atoms.
Then I have a question.
Yes?
Does it only create thermal energy when the bonds break?
With the what?
When the bonds break, isn't that...
No, when it bounces. We're talking about ideal elastic collisions. So no energy is spent anywhere. But here is totally inelastic. So it goes bam and it stops. So energy should go somewhere and it cannot go to bouncing, right? So it goes instead goes inside the object itself and actually the ground too. Actually there are two ground is consisted of molecules either, right? But for simplicity we just talk about one object, for example. So one object, it contains, remember this Avogadro number? Avogadro number, it is the amount of molecules in 1 gram mole. 1 gram mole. So it is the amount of grams that equals to atomic weight, right? Like for example, for hydrogen, gram mole is 1 gram. For helium, atomic weight is 4. It is 4 grams. So it's different for each element, right? For oxygen, I think 16, so 16 grams, something like this. So you have Avogadro number. If you know gram mole and you know the amount of like what is kilogram or how many is in this object, what's the mass of each object, you can calculate the number of the molecules there. And each molecule have this heat energy. It comes from physics, equal 3/2. Oh, sorry. Each molecule has this energy in average, because molecules are moving sporadically, in all directions. They collide, mostly elastically, so they collide, go further and further and further in many ways with the high speeds.
Average.
One of the example, which one of the tests that you ask you the questions will be calculate the speed of the molecule. So think about it. So this is average speed. This is some average speed and some temperature. Temperature is for average speed, average energy of each molecule. Average.
And what is K?
Say it again. This, yeah, I will tell. Yes, T is a temperature which is measured in Kelvin grades or Kelvin. Kelvin, it means that minus 273 grades of Celsius. It is equal 0 Kelvin. Or maybe I correct like this. So this temperature scale has the same measure of the same grade, but the 0 is moved to minus 273. It's called absolute zero of temperature. Because at this temperature the movement stops. No movement at all. They stand. The molecule will stand. Actually, it's not like this, but this is classical physics. So, and remember this thing, this is a very important formula, which connects energy of the molecule with the average temperature. So temperature is actually average energy of average molecule. This we just remember and then go further. Any questions to this? Average. Remember, it's average. Because some of the molecules are very fast, some are very slow, but average you can calculate. And the calculation gives this. And K, it is called Boltzmann constant. This was a famous guy who actually is the founder and father of the whole so-called statistical mechanics and heat physics, thermodynamics. It's called thermodynamics. So it's about heat engines and everything about. And his name was Ludwig Boltzmann. He was an Austrian scientist, and around 186.6, so it is at the end of 19th century, he derived a formula which is so famous that it is engraved on his tombstone. So his tombstone, Ludwig Boltzmann, it has this formula. I will write for you. S equals K, which is constant of Boltzmann, K is, you can look into this. I forgot myself. What's this amount?
What's S?
Just a sec, I'll tell you. Yes, did I write it? Okay. Okay, okay, I found it. 138. Right. So the constant 1.38, 10 to the power minus 23 joules divided by Kelvin grade. So if you see the previous formula with the energy, you see that K connects it connects temperature with the energy. Remember?
Yeah.
Temperature is the average energy of the molecule, right? So this constant, it just connects joules are the measure of energy, with the Kelvin, which is a measure of temperature. So this is transfer this and back. And this formula, which was derived by Ludwig Boltzmann around something this, it gives you another thing. It connects actually exactly it gives you S, and S is measure of disorder or chaos. It is called entropy.
Entropy?
Entropy. So the bigger is the S, the bigger of the entropy or the chaos in the system. And it's very important. It's a very important thing in physics. We'll talk about this later more. So what he calculated here, actually, just in short, W, it is a number of so-called situations that can happen in the system.
What? Simulations?
Situations.
Situations?
Yeah, or configurations, like for example, like so many molecules, you have lots of molecules, right? Avogadro is a huge number, right? 10 to 23, 10 to the power of 23. So, by the way, here is minus 23, it's because of Avogadro number, by the way. But anyway, so so it is lots of molecules, right? And they can be configured this way or another way. They're running sporadically, you know, moving this and this and this chaotically in different ways. So they can have many configurations. And if you calculate lots of this, all of these configurations, you will get this number W. So this is the amount of configurations. Log, I forgot. Did we talk about this function or not?
No.
So log is inversion of the function of exponent. So
2 to the power of n.
huh?
2 to the power of n.
2 to the power of n, it is like exponent, right? For example, it is n, like for example, right? But if we take an inverse, we want to find n from this formula. If you want to find this, you will write n equals to log by the base of 2, because here is 2, of n. So log is inverse to exponent. As the function inverse, remember we talk about inverse functions. They are symmetrical along this line, diagonal line, y equal x, if you remember. So it's inverse function. So if you have this n is an exponent 2 to the power of n, right? And if you want to find n, the number of steps in geometrical progression, you should use this function log. Log by the base of 2. It's called base of the logarithm. The log is a short for logarithm. So that's what's about this formula. So what it gives you, the formula? This is a number of...
What is W? Oh, the degrees of freedom?
No. W is a number of all micro configurations that can be in the system. All the configuration of the molecules. There can be many.
Isn't it the same as degrees of freedom?
No. So it gives you from amount of configuration, it gives you the measure of disorder. And the interesting is that
Is it like a combinatorial number of configurations? Just how many ways
you can look into it. As we were not talking about this, there's lots of formulas for to calculate this thing, right? But for example, like 0 and 1, like what can be configuration 0, configuration 1, right? So how many configuration? 2, right? So log by the base of 2 from this. What is it?
Oh, log of 2, 1.
Log of 2, 1. So it's one bit. That's all. Log of 4, it is like 2 bit, right?
Yeah.
Log of 4, 2 bit. So it is connected with information, definitely. And actually, what is found out that this amount of entropy as a measure of disorder, it actually connected with information. So entropy, like this, with this formula, entropy is often called information. I'm sorry. Information is neg entropy. So anti-entropy.
Hey, Dino, what does neg mean?
Neg means negative. Simple. Negative. So if we're talking about number of disorder, measure of disorder, right? It's negative to measure of the order. So information from here, information is a measure of order of things. And now we come to information. There's another guy who lived in the 20th century, and somewhere in the middle of the century, his name was Claude Shannon. He was an American, probably of maybe French, some French parents or something. I don't remember this. So it's in the 20th century, and he is the founding father of another very important theory, which is called information theory. So he actually understood, at least comes closer as anybody before, to the understanding what information is. And from his understanding of information is what is called sometimes surprisable. Surprise. So surprise me, right? Surprise me. So if you like, if you how this called coin.
Flip a coin.
If you flip a coin, right? So it may give you odds or how they call them this?
Flip a coin?
Yeah.
Yeah, you flip a coin. Head or tail?
Head or tail. Head or tail. So you can have only head or tail or 0 or 1. Like for this maybe tail, right? And this is head. So you flipping a coin, which is goes. And when it falls down, right? You're surprised. Some of this come 1 or 0, tail or head. So surprisal. And what Shannon postulated, he said, it's a postulate actually. He said that when you're surprised by this surprisal, a flipping of coin, and it gives you tail or head, whatever it gives you, but it gives you some information that the coin fall down with the tail up, right, or the head up. It's some information. And this information contains exactly 1 bit. This is a definition of bit. This is definition of 1 bit. Flipping of a coin, so surprise. If you do something more complex, you can still calculate other things, and how it goes, we'll talk in short, like right now. Now we'll talk about something that is called evolution. Surprise, but evolution. Or survival of the fittest. You know this term?
Like Darwin?
Survival of the fittest.
Oh,
So-
that, yeah.
Yeah, so evolution goes by the survival of the fittest, for the stronger one, right? But it's something else. It's closely connected with information and all that we talked before. So if you remember, we talk about quantum. What is quantum? Quantum is a loop in time. So what happens? Object goes, this is time, and then it returns to itself. This is anti-time or space. It's the same as we say that object moved from one place to another. So it takes over the space by this time. Time, space. When it returns to itself. Because here it's the same to say as the object preserved itself. So the same object, but in another time and in another space. But because we have this loop, we have these 2 identical objects. We can look at them like 2 identical objects here and here, like just pictured here like this, like in a loop, right? If we come here, so we have 2, but then then the time is running further and further, but now here we have already two objects, because this object may remain and this object may be here. Maybe it may disappear in some case, but goes here and then. So because these loops are returning back and back, and each of the objects can double itself again. Remember, when you're returning, when you're going back to space, you will meet with yourself, right? Or if you maybe remember inside, if you try to remember or think about yourself, you meet with yourself, you see yourself, but in the past. Because when you remembrance takes some time. So you remember yourself not now, but just microsecond back. And you can do it many times. You can recall like microsecond ago, 2 microseconds, whatever, how your life was going. So you remember. You have a memory. You have a memory. And memory is information. So what is going on here? When we're returning back and back, each quantum returning back and back and back. What is going on? The first beginning, the first quantum, position 1, right? It returns to itself. It has 2 positions. 2 positions now. We can say this 0 and 1. Like for example. So it returned. It's the same quantum here and here. It's just when returned, it has current position, and the previous position in his memory. And each of these positions can go and loop again, and again, and again, and again. So those are loops. Loop, 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 all of them are loops. Just pictured like a tree here. And if you want to calculate this n number of these events of looping, right? We have total number here, like many results. We have this n results. So when you have doubling, this is a geometrical progression. So n, the simple way is to write it like this, right? This is the formula for geometrical progression. So when you have doubling, and each loop is doubling, each loop in time is doubling. So here we doubled, there is 2, there is 4, then 8, 16, further, and to the end, like 2 to the end. And again, just to repeat, if you go back, it is like this. Inverse formula to find out n from n, n small from n capital, till like this. So here is n. So what is this? This is actually a tree of evolution. This is tree of evolution. Evolution can be of many things. Quantum evolution, the evolution of quantum, your own evolution, how you evolve. You think about something, or you do something, you come to something and you think, okay, should I eat this tomato or not? You decide, right? When you decide eat, you got one bit. It's your decision. There's a fork. There is one decision which did not survive. You didn't eat. You decided to eat tomato, right? So one case survived. The another that you're not eating tomato did not survive. What was the question?
Does your memory actually have a certain amount of space?
About what? The base?
Does your memory actually have an amount of space that it can hold, like an amount of memory?
No, just you see, the base depends upon how many choices you have. You come and you see, like, for example, not tomato or no tomato, right? To eat tomato or not to eat tomato. But you may have, like, for example, a pickle. So you have more choices, and the base changes then. Base 2 is because you have 2 choices. If you have more choices, you have like more of this. So you can talk about this later with your dad on this. It's pretty simple. So many choices, just the base changes, but the idea is the same. The formula is actually the same, just different base. So here will be not 2, but like a 3, 4, whatever. With them. So this changed the base. This and this are the same. Just if you go, you think about this. Now let's take a look at this picture. Why this picture of evolution? This evolution of us. We talk about this, right? We think, we remember, we make choices, we go further and further and further and further. Maybe the choices may be more complex than just choosing between 2, maybe choosing between more, so just change the base, but the formula is the same. The same thing goes with evolution, like of the species, right? The same thing. Like, for example, in simple way, one species, right? It multiplied, like whatever, rabbit, whatever, and it multiplied it, and his eyes may be darker or lighter. Like here is darker, here is lighter. So there is a choice, right? Or maybe this one is stronger, or this one is stronger, and this is maybe weaker. Which will survive? Stronger, probably yes, but if there is a lots of food, but if there is not too many foods, weaker, which consumes less food, will survive, right? So it depends, but this is how goes evolution. Yes?
Are you talking about natural selection?
Yes, natural selection, yes. But natural selection is not only survival of the fittest. Natural selection goes not only like in the evolvement of the animals or whoever, or evolution of a certain person, right? But it goes in the quantum world too. It's the same thing, because some of the things, some changes, like the time running, time produce changes, and changes mean information. So the time runs these loops in time, produce more and more bits of information. And when this time goes, you see the evolution, because some of the changes may be positive for the quantum, right? So maybe they allow him to survive. Another does not. Maybe he goes this direction, choose between this direction and that direction. This direction goes to the empty space where quantum is okay, and another goes maybe into the black hole, which it disappeared there, right? So different choices produce different ways of survival. So when you look, look from the point here, from the first point. This is called objective frame. We look how it goes in the nature, in the material nature. Goes objective frame. So what is going on? This or this way, this or this way. Some of them maybe this disappeared, so all these branches possible they disappeared, right? This survived, then maybe this disappeared, so all these branches are disappearing. So you understand, right? What is going on? So all these dying, and this line, for example, is the only survival. So this is survivor. And who is the survivor? Who is the survivor? All the rest are dead. They disappeared. Like by this way or another way, they for some reason they didn't make it. So one survivor. Survivor is observer. Is the guy or quantum who may look at the universe and see what is going on. So, and we are survivors. Like we are talking now because we survived. All our ancestors here, they made the right choices. They didn't make the wrong choices. And also, the right choice is not exactly that the choice may give you like death. No, maybe some of them will be alive, but the only particular one choice makes you. Think about this. There's only one way. Yes, I'm answering your question. There's only one way in this picture which comes to you as an individual. To each of us. Each of us has its own way of survival, like our parents, our ancestors, our choices in life and everything like this. So we look from here, and this particular point is called subjective frame of reference. Yes, what's the question?
I did that.
Mm-hmm.
But it's possible to know if this was the best outcome because there's probably like 100% chance that there is a better outcome for this, but there's no way to be sure what is the right decision and what is the bad decision, because the bad decision can lead to better outcomes still.
Oh, you don't know for sure. Yes, it is difficult. This is the point of science. Actually, you should make a very serious research how it goes, and we don't know exactly in reality how it went, right? So we don't know for sure, but many of things can be calculated this way, and going down, simplifying to the choice of double between two. That's why computers can work on this binary system, because everything can be derived to this base of 2. So just choose simple choice 0 1 0 1 0 1, but it goes further, and you can calculate the amount of information and everything. So just to finish with these abstract pictures, right? Objective frame, what it gives you? Objective frame gives you all the possibilities. That there may be this possibility, this. We can think that some of them are not reliable. They will disappear in the future. Some of them may be more reliable. They will live for some time, right? For this time of steps, amount of steps, right? And some of them less, some of them more reliable. And we know that only one gives you particular. If you already know who is that you, this subject, like me, I said, okay, let's calculate it for me. Or Vitya said, I wanted to calculate for me. So this is for Vitya, this is for me, whatever, but it's individual. So you can see your line of ancestry, right? Your ancestry tree, or genealogical tree, right? In generally speaking. So you can calculate it somehow. And when you're looking from you, particular you, it is your subjective point of view. This is your subjective frame of reference. And it's very different from the objective. Objective gives you all the choices. And there are n choices, n capital. Lots and lots. Like even number of Avogadro molecules in our body is 10 to 23 multiplied by the amount of our weight. Right? Okay, question?
No question.
Okay, no question. Okay, so just have it in mind that there are two very important points of views or frames. It is objective frame, which is mostly the frame of reference of material science, materialistic science. And there is a subjective point of view, which is the point of view of every one of us. We are living inside us, right? It's our, and we look at in the world through our eyes only. Your eyes individual are different from any each other, unique. And this subjective point of view is very important for us, for each of us. And unfortunately, science does not think a lot about it. But I can tell you that most of the main founders like of quantum physics and Einstein, Bohr, all of them, Heisenberg, all these guys, they were talking that sometime there will come the guy who will create the theory which combine objective frame and subjective frame. So we'll include human into the theory. And it looks like that time is coming step by step. That we were talking about. And also, interesting thing, if you look at this, amount is n, right? So what's the possibility now? Remember this probability. What's the probability that survivor is you? The amount is n, probability, I will say, it's just 1 divided by n. So how many chances? 1 of n, right? One chance of n. So 1 divided by n. This is your probability. And the same is connected with information. Remember this?
Yeah.
Because this is amount of states. There are amounts of situations that may happen. This kind of individual, this, or quantum, this, or this, or this, or this. So you can calculate from this amount the information which is actually needed for this. And if you look at this, you see the connection between information and energy. This thing, in the beginning, it contains some energy as a potential to make changes. To make change, energy make changes. This choice or this choice, this choice or this choice, or this choice or this or this. This is what energy does. But when it makes the choice, and for you, for your particular subject, for you individual, as individual, the choice is already made for all your billions of ancestors. They are made. Or if in your life, you're talking about your life, if you look on you to all your choices through your life, so again, all choices are made and you survived. So the choices are not that bad, right? You can calculate information which actually was produced by flipping these coins each time. One flipping, another flipping, another. Each choice is a flipping of the coin. And you have connection between probability and actually thinking what to do. Your choice, your free will. So evolution goes to free will, which from objective point of view looks like probability. Just chaos, chaotic thing. But it may be not chaotic, maybe you're free of will. And I will finish with this very important formula which we will use in your calculations. Again, this Ludwig Boltzmann, he created this thing. I will write it for information, right? So he created this, ds equals dE divided by kt. K is a constant, Boltzmann constant. S is entropy, E is energy, T is temperature.
What is S is entropy?
Entropy is a measure of disorder. So
S is
information is minus dE divided by kT. So what it means that if you add the energy to the system, the entropy goes up. And if you add information to the system, energy goes down. So in other ways, if you want to get information, you should waste some energy to that. You should put some energy. So you should release some energy from you. You should use some energy that you have to produce information to you. Each of the choices go into the tree of evolution, whatever quantum or your own, or maybe your species. Each step needs energy, and the energy is calculated by this formula, D of course. This information. You see, it's interesting thing. Information, and this is very important formula. Information is directly connected with the energy. It's the formula, physical formula. It is used. It's not only just a formula. It's very useful in the supercomputers today, because when you erase information, like you have that in some memory cell, right, in supercomputer, and you have in this memory cells lots of unneeded information that you don't want anymore. You want to erase it, right? And when you erase it, you deliver some energy to it in the form of heat increase. I forgot the term, but it's look at informational heating. So when you erase information, it adds heat to your processor. So to do that, they suggested some other processors which are not erasing information at all. What they do, instead of erasing, then just move it to other memory. So they have lots of memory cells which are actually contains this in unneeded information. It looks very similar to what we have in space. Space is a storage. Memory storage, space. Memory storage of information. Needed or unneeded, we don't know, but it's there. It's not eliminated, it just moved. Just for you. And this formula I would not derive here. It's a long way to do it. We would maybe, if we have a chance, maybe we'll do it. But believe me, it is the formula of the modern physics, current physics. It's not the future physics. And I will ask you to use this formula to calculate certain things in the test. So, what questions? I hope that by listening to this, at least you have some clue how close the modern physics come to the informational science. It comes very close, and the only step officially is not done. That's what I'm trying to do. I'm trying to explain you something, but even from the current state of physics, you should understand that information is in the core of modern physics. Okay, guys. Ready to write questions? Oh, maybe I will write one more thing. To produce to produce work is to transfer information. Just remember that, because each time you're doing something, even mechanical work, you produce information and you store it in the in the process that you actually did. This is the storage. The result of it is the storage of information. There's also, think about it, there's also this T, temperature, right? A temperature is connected with the stochastic chaotic movements of molecules. And these movements, they contain unpredictable things. You don't know where it goes, right? So it is sort of indeterminate, right? Not indeterminate, sort of indeterminate factor. So T is the adjustment to this indeterminate factor. So the more temperature, the bigger is indeterminate factor. If T was equal like one degree, right? So dE will be totally, dI will be totally dE. Remember this formula? That's like previous I wrote. So if temperature is 1, it will be exactly equal to energy. So information, it is energy. Just in the real calculations, we need to understand that there are certain indeterminate or undetermined energy connected with the molecules. And because we don't know them, but we know how to measure them by temperature, right? So we use it in the formula. And that's why information amount is a little different than just energy. So you ready to write the questions? If you don't have your own. Okay. This is the next one. The next one, I hope, will be about heat machines and how machines work in general, like this machine too, Kalashnikov machine. Okay. Okay, now you're ready, right, to write? Okay, the first thing is, at what height can the energy in the cup of the boiling coffee?
Wait, can the energy of boiling coffee?
At what height can the energy in the cup of boiling coffee lift your own car, your dad's car?
Hour, you know, how much is a car weight?
2 tons.
2 ton, 9-year-old still don't have this car.
Good.
So in short, like if you want to use the energy that is in the boiling cup of coffee, right, to lift your car, so how high can you lift it with this energy in the cup of coffee? Okay? And the sub question to this, how much information can it produce, this energy? How much information can it produce?
Is this all one question?
Yeah, this is one word, because it's similar, right? You calculate energy, you can calculate these formulas I gave it to you. But the question understood, right?
Yep.
Okay.
Okay, I'm ready.
The second is, what velocity have an average molecule of in boiling water?
Listen, make sure you put a line between questions to separate.
Yeah.
That's it. Let's get it quickly.
Can you please repeat it? Can you please repeat the question?
Sure. What velocity have an average molecule in boiling water or coffee?
Okay, Dinner, we're ready for the next one. Is it that a formula?
Yeah. This is just this is for the next question. So you got this, right? Add to this question, to this, compare this speed, this velocity, right, calculated, compared with the speed of sound. And speed of sound is about 330 meters per second, but you can find it on the internet, right? So compare this velocity calculated with the speed of sound. This later. I'll adjust this one next question. So next question, right?
Wait a second.
Sure. Ready? Guys?
Connor's still writing that.
Okay.
We're done.
Okay, next question. How much information contains in full tank of gasoline of your car?
Wait, is this a fourth question?
This is question.
Is this a fourth?
Third.
This is 3. This compare with speed of sound, it was 2. It's just addition. Okay?
3. Okay, what's question 3?
How much information contains in your full tank of gasoline for your car?
How much information is contained in the whole tank of gas?
Yeah.
And to know that, you should know the volume of the tank, right? I hope your dad knows. But also you should know that 1,000 calories is actually a measure of energy which is produced when you burn something. Calories is a heat, like a heat energy. So it's called 1 kilocal. 1,000 calories is 4,184 joules. Joules is the measure of energy, normal. Just write it. 1,000 calories is 4,184 joules. Done? Okay, now the last question, this is the fourth. This is the important lesson, so please try to do it accurately, all these examples, okay? And think about them, talk. And all that. Okay, ready?
Yeah.
How many calories? How many calories you will have to consume with food? Because food contains calories, you know, right? And calories are energy.
I know.
It's a chemical energy actually which is producing everything in your organism, right? In your body. So how many calories you will have to consume with food to replace your energy loss by doing mechanical work Okay, by doing mechanical work of, you ready, right?
Yeah.
Pushing your house wall
Your house wall
with a force 50 kilograms.
with
Calculate how kilogram force is.
what? What's the last part?
Antosha should know. With a force, pushing the wall, the house wall, with a force of 50 kilograms.
50 newtons, 500 newtons.
It's not, yes, 500 newtons, right? Almost, yeah, 500 newtons. You mean, yeah. Pushing for 10 hours.
Oh my god.
Oh my god.
So calculate what kind of thing for 10 hours.
But no work is done, the wall did not move.
And whatever, I don't know, just calculate it. And how much information you put into this wall. Ready?
Wait a sec.
Yep.
Okay, I'm done.
Okay, good. No questions?
No, no question.
Okay, so
Dude, I'm not done.
not done, okay. What?
Just ending the, Data was just ending the recording.
So you done, right? Okay.
No,